this computer. Share. Well, the next lecture will be the fast Fourier transformation, and this time decimation in frequency. Decimation in frequency. Now, we said that Wn, okay, Wn k e to the minus j 2 pi k over n. This will be the weighting function. Decimation in frequency, really, in this time we are going to arrange the sequence as it was. Okay, so let's go directly to the sequence configuration without talking about these equations. Okay, again, we have even and odd parts, but in this time with a new way. Let's go to the yes, look please. Now we are going to arrange the equation or the sequence, okay, as x of 0, 1, 2, 3, 4, 5, 6, 7. Now, without what? Without subdividing the elements into even and odd parts. But look, here we have the points are colored. Please look. This will be x of 0, x1, 2, 3, and then 4, 5, 6, 7. The sequence is divided between two halves, okay? First half, which consists of the first 4 elements, and the second half, which consists of what? The last 4 elements. Of course, here we are talking about what? About the 8 points FFT. So first of all, we are going to calculate the A values. Look, please. X of 0 plus x4. This will be A value. Okay, and then B of 0 will be x of 0 minus x of 4. Second time, x1 plus x5. Just addition and subtraction, no more, no less here. x1 plus x5 and x1 minus x5 to get B1. Then B2 will be x2 plus x5 and B2 will be x2 minus x6. In this time, we have what? We have simple operations. I mean, just addition and subtraction in the first stage. Finally, we have A3, which is x3 plus x7, and B3, which is x3 minus x7. Now, by now, the first stage is finished, okay? It is very simple and easy. We said that the sequence will be, in this time, just as dividing the sequence between two halves, first half and the second half, and then we are going to perform the addition and subtraction with the first element from first one and the first element of the second one, and then, okay, continue up to getting the end of the two sequences. Well, so we have what? We have a set of A values and a set of B values, A0, A1, A2, A3, and B0, B1, B2, B3. Of course, B values represent the subtraction between x0 minus x4, x1 minus x5, x2 minus x6, x3 minus x7. These are the values of B's, and the values of A are what? Are the addition between x0, x4, x1, x5, x2, x6, and x3 with x7. These are the elements of the first stage of the FFT. Then we have n over 2 point DFT. Of course, n over 2 point FD, here we have 4 points. I mean, we have 4 points. Sorry. And here again, we have 4 points again. Well, so 4 points by 4 points. And finally, we have what? We have the last values of the signal. Now, let us talk about this one. Now, what do you mean by n over 2 points. Okay, what do you mean by n over 2 points? Now we are going to go inside this machine. And what do we mean by this machine? Okay, now let us illustrate what's going on. Well, now we have 4 points. Okay, 4 points FFT again. In this time, x of 0 plus x2 and x of 0 minus x2, x1 plus x3 and x1 minus x3. Okay, this will be the first stage. Of course, then it will be multiplied by W41. This is the way by which we can calculate what the decimation in frequency. Then it will be n by 4. I mean 2 points FFT will be the last point, last stage. Same thing for the lower panel. Again, we have, just as we have calculated the 4-point FFT. Okay, 4-point FFT, and then we have 2 points, 2 points. Okay, look, 2 points, 2 points, and this will be the 8-point FFT. Now, this will be the decimation in frequency. Of course, what is the difference by now in these two techniques? In the first technique, I mean the decimation in time, we have what? We have arranged the element and divided the element into two groups. Okay, first group of even elements, second group of the odd elements. Then we have performed some calculation and multiplying by the weighting functions, then getting what? Getting the final result. Now look please here. And the output in the first case, I mean the decimation in time, the output is arranged as what? X of 0, 1, 2, 3, 4, 5, and so on. So the output is arranged in is sorted. Now in this time, I mean the decimation in the frequency, the output is not sorted. Look please. First output represents X of 0. The second output represents X of 4. Third output, X of 2. Fourth will be X of 6. And here we have X1, X5, X3, and X7. Okay? So in this time, the output is not sorted. Okay? So you have to take, for example, X1, X0, X1, X2, X3, X4, X5, X6, and X7. So you have to arrange the output at the end of the calculation. Using the previous algorithm, by now we have an important thing, really, you have to keep in your mind. By using the previous algorithm, the complex multiplications needed is only 12, while using the normal DFT would require 64 complex multiplication. Now, can anyone tell me what's the difference between the ordinary multiplication and complex multiplication? Can anyone tell me what's the difference between multiplication and complex multiplication? Can you hear me or not? Jamaat? Well, okay. Now let me show you what do you mean by the multiplication and the complex multiplication. There is no response. I don't know why. Okay. Now, for example, if you are going to multiply A by B, it's called what? It's called multiplication operation. For example, say we have variables, say, for example, we have two variables, x1, which is A plus JB, and x2 equals C plus JD. Okay. Now, if you are going to multiply x1 by x2, what does it mean? It means we are going to perform what? The complex multiplication. Okay, this will be complex multiplication. Well, now this will be the complex multiplication. I mean, here we have a plus jb multiplied by c plus jd. A by c plus jbc plus JAD minus what? Minus BD. Okay, so it will be the following. I mean, I'm going to add AC plus J multiplied by BC plus AD minus BD. Now the important point here, how many multiplications we have? AC is the first multiplication, BC second, AD third, and BD is the fourth. So every one complex multiplication, every one complex multiplication equals to 4 multiplication operation. Equals to 4 multiplications operation. Okay, this will be the relationship between complex multiplication and the multiplication operations. Now let's go back to the slides of the PowerPoint. Well, so in general, complex multiplication of DFT is equal to n squared. Okay, is equal to n squared, while the complex multiplication of the FFT will be n over 2 log 2 n capital. Of course, log 2 means ln of n capital over ln 2. Well, ln of n capital over ln 2. Of course, now say n capital equals to 1 kilo samples or 1
سيدة
بله.
بس أولاد عبد الستار سيدة زومين وكان وضابط وساعات طائق يخرج تضرب إنه كان زات مشكلة وتشابوين وضابط
ايه مشكلة
وجا قوتي بيش طاب صانت
بالله سر شابه
ممنون
سر شابه خيراتي. Okay, now n capital is 1024 points. 1024 points. If you are going to use the DFT, ordinary DFT, so the number of complex multiplications will be n squared. Okay, so it is 1,048,576 complex multiplications. While if you are going to follow the approach of FFT, either using decimation in time or decimation in frequency, at that time, the number of complex multiplications will be reduced dramatically and becomes 5,120 complex multiplications. Now, what we can conclude from this calculation, of course, using the fast Fourier transformation, this will lead to speeding up the algorithm of the FFT and reducing the number of complex multiplications. Now, to determine the output correctly of the decimation of frequency output, now we have the input data index, which is 0, 1, 2, up to 7. Index bits, of course, if we are talking about 3 bits at that time, I mean 8 points, it means 3 bits, 3 zeros, 1 0, 0 1 0, 1 1, up to 3 ones. Now, to determine the output, we have to follow this approach, which is called reversal bits. Okay, reversal bits. So what will go into reversal bit now? The last bit will be where will becomes inside instead of the first bit. Okay, last bit becomes instead of the first bit. So okay, indexed bits. Okay, and we are going to apply the reversal. So this one, okay, I mean first one will be first bit becomes instead of the last bit, and the last bit becomes instead of the first bit. So we are going to what? We are going to switching between the first and last bit. Look, so the 1 becomes 4, 2 will stay 2, and the 3 becomes what? Becomes 6. Okay, now moving first one to the last one and last one to the first one, 3 becomes 6, 4 becomes 1, 5 stay 5, 6 will be 3, and 7 will stay 7. Well, in this way, we are going to what? We are going to apply the bit reversal, okay? The bit reversal approach to determine the correct output. Now, we have an example which is talking about decimation in frequency. Now, here we have 4 points, which are 1, x of 0, 1, x of 1, 2, x of 2, 3, and x of 3 is equal to 4. X of n, of course, equals 0 elsewhere. Find the DFT for the first 4 points, of course, using what? Using the decimation in frequency. What we are going to, in this way, we are going to directly align the elements without subdividing. Then we are going to perform the addition between. So after that, we are going to what? Just as dividing the whole sequence between 2 parts. First, a part that represents half of the points, and second part represents the second half of the points. So first half will be 1 and 2, and second half will be the 3 and 4. So first of all, I'm going to perform the addition between 1 and the 3, which is 4, and then the subtraction, which is 1 minus 3 to be minus 2. Again, the same thing for the last 2 points from each group, 2 plus 4, and 2 minus 4, and minus 2. Well, up to now, we have performed the first thing. Now, in the second time, we are going to what? We are going to perform the n over 2. And then here we have 4 plus 6 will be 10. And 4 minus 6 will be minus 2 multiplied by what? Multiplied by W40, and it will be minus 2. W40 will be what? Will be 1. Now, the second thing will be what? Will be the second part. In the second part, we have the following: minus 2, and in this time, this point will be multiplied by W41, which is minus j. Okay, minus j. So minus j minus 2 will be j2. Okay, so minus 2 plus j2. And here we have minus 1 again, minus 2, minus 2j. But the orientation of the elements, we have to what? We have to follow the bit reversal operation. Of course, how we are going to do so? Let's go to the whiteboard to show you what do we mean by the bit reversal here. By now we have only 2 bits, so the operation of the bit reversal will be easier. Look, here we have the input. Okay, the input 0 0 1 0 0 1 and 1 1. Okay, now applying the bit reversal, first one will be 0 0, which is x of 0 as output, while here it will be 1 0, and it will be x of 2, and this one becomes okay, this one becomes 1 0, and here we are 1 1, so it will be x of 1 and x of 3. Okay, so let's go back to the PowerPoint slide. Look, x0, 2, as I've told you, 1 and 3, by applying what? By applying the bit reversal technique to determine the suitable output. second thing, by now we have talked about the example and how we have calculated the example. Of course, it's very simple and easy. All you need is what is to try to do the same thing by your hand on a piece of paper for training. Otherwise, it will be a difficult job. Now, to determine the inverse Fourier transformation, again, we are going to follow the same approach as we have done in the calculation of the fast Fourier transform, except each W will be replaced by W conjugate, and the final stage will be scaled by 1 over n again. Okay, you can see, as you can see here, we have the 8 points FFT, x of 0, x1, 2, 3, 4, 5, 6, and 7. Now, assume that you have a line between the first half and the second half, and then we are going to perform the addition between x of 0, x4, x1, x5, x2, x6, and x3 and x7. Okay, to get what? The first 4 points. Perform the subtraction between x0 and x4, x1 and x5, x2 and x6, x3 and x7 to get what? The b values. Then we have what? We have the 4 points FFT and then 2 points FFT. And finally, the final scale, as you can see, the final stage is scaled by 1 over n. And you can see the all weighting functions, I mean the W's, are what? Are scaled or calculated as complex conjugate. Okay, complex conjugate. I mean each j is replaced by minus j, or each minus j is replaced by plus j. An example about the inverse Fourier transformation by using what? By using the decimation in frequency. This will be x of 0 is given 10, x of 1 minus 2 plus j2, x of 2 is minus 2, and x3 is minus 2 minus 2j. So what we are going to do, of course, the same thing we are going to follow, just as subdividing this sequence between the first 2 and the second 2 elements. By now, we are going to perform the addition between x of 0 and x of 2, which is 10 minus plus minus 2 will be 8. And then 10 minus minus 2 will be 12. Okay. The same thing for x of 1 and x of 3. It will be minus 2 plus j2 plus minus 2 minus j4. As you can see, due to this addition, the 2j with minus 2j will be cancelled. The remaining will be minus 4. And then we have the minus 1 operation. I mean minus 2 plus j2 minus 2 plus j2. Of course, in this time, it will be plus 2 plus j2. So the remaining will be j4. Okay, j4 will be the remaining. Okay, now next step is to calculate the 2 points FFT. Okay, 8 plus minus 4 will be 4. 8 minus minus 4 will be 12, and multiplied by W4, 0, of course, 1. Lower panel, we have 2 points, which is 1 and j. We said that when we calculate FFT, will be minus j, but when we calculate inverse FFT, it will be its complex conjugate, and complex conjugate of the minus j to be j. Now, j by j4, it will be minus 4. Okay. Now, minus 4 plus 12 will be 8. And 12 minus minus 4, it will be 16. Now, this will be the output stage of the inverse, but we have to what? We have to scale down by n, I mean 1 over n, 1 over 4. And then we have to apply the bit reversal. I mean the 0 stays 0, but the first element means it is the output of the second element, and the third one will be the second element, first element, and we have the third one, which is 4. So it's 1, 2, 3, 4. Okay, this is about what the decimation in frequency fast Fourier transform. Of course, this is a very important topic. I mean the calculation of the FFT. using the decimation in time and using the decimation in frequency. And you have to be careful because this will be used in the determination of the signal components in the frequency domain for the discrete time signals, of course. Do you have any questions? Is there any question, please? There is no response. It's a bad response, really. And I will recommend, I will submit some recommendations for the department. You are always busy with the microcontroller and there is no other subjects. Today, I'm going to ask the department to do something for you, really. It's not acceptable. Exactly, you have at least one question about the fast Fourier transformation in the final exam. Okay, in the final exam, at least you have any question about the fast Fourier transform. So you don't have any questions. Okay, don't mind about it.
سعيدة دنجمتت سعيدة.
يعني شو بكم دنجته؟ بري چارگه کی هزار جاره من گود. اوا complex فرق چی انا بینی multiplication و complex multiplication. يعني معاد كسك نقول مثلا تشتك جماعات كاني جماعات كسكي هي كسكنينا يعني معقوله بس دي كونت كتقل زومي وخلاص شو ابدا معقوله يعني همي مجيلن بمايكرو كنترولر همي مجيلن
والله سعيدة اسمه حوزري بس سعيدة مايكرو تش سعيدة
يعني معقوله بس مايكرو كنترولر لا بس مايكرو كنترولر ميتين ابا بيسارك ببيجمته ابا اكيد بيسارك هي لسر fast Fourier transformation in the final exam درسته. Okay, as you wish, as you like. I don't mind about it. Now, let us أخير تشت منها هي طبعا. Okay. Let us talk about the axis of the frequency. I mean, what do you mean by the K and the value of each K in the frequency domain. Now, this will be the axis, and this is the K axis. Okay, and this will be the K axis. X of K. Now 0, K equal to 1, of course, K equal to 2, K equal to 3, 4, 5, and so on. Of course, using this technique, it will divide the scale into what? By KFS over N. Look, please, what I mean about this thing. KFS over N capital. Okay, KFS over N capital. I mean the sampling frequency. The sampling frequency will be divided by what? By the N capital. N capital represents the number of FFT points. Okay, N capital represents number of FFT points. Okay, number of FFT points. Now, for example, if you have 1024 points at that time, the resolution will be increased. Okay. Again, if you are going to more increase the number of points, for example, say 2048 points, again, it will enhances the resolution. So we have resolution delta F will be Fs over N capital. Okay. So whenever you are going to increase the number of points, you will get what? Better resolution. Now, the frequency of every point in this axis, for example, this one, I mean 1, will be what? Will be Fs over N. Second one will be 2 Fs over N. The third one will be 3 Fs over N, 4 Fs over N. Of course, when you talk about 2 Fs over N or 4 Fs over N, it represents what? Real frequencies. So you may have a component at this point, okay? Component at this point, it means what? It means you have a signal with a frequency equals to 5 Fs over N, okay? I mean 5 delta F. What does it mean? It means that the axis of the frequency becomes what? Becomes multiple of what? Of delta F. يعني 1 delta F, 2 delta F, 3 delta F, 4 delta F, and so on. This is what? This is an illustration For what do you mean by the calculation of x of k? Look, x of k is the y-axis and k represents what? The x-axis. Of course, every value of x of k represents real frequencies after what? After determining the sampling frequency. So if we have the sampling frequency at that time, the x-axis or the k-axis here will becomes what? Becomes delta f and its multiples. So in other words, we have the following axis. Look at the axis. It will be as follows. Now this one delta f, 2 delta f, 3 delta f, 4 delta f, 5 delta f, and so on, and this will be the x of k. By now, what we are going to conclude from these lectures, we have two ways to calculate the fast Fourier transformation. And the fast Fourier transformation is an algorithm or a technique used for what? Used for speeding up the DFT calculation and reducing the multiplication operations. So, in other words, simplifying the system structure. Second thing, we have two ways to perform the fast Fourier transformation: decimation in time and decimation in frequency. And as you can see, the final thing, the x-axis becomes what? Becomes in terms of delta f and its multiples. In other words, increasing the number of DFT points will enhancing the frequency resolution, hence sensing more frequency values, or becomes more accurate in the values of the calculated frequency components of the input signal. This is about for this week. Inshallah, next week we are going to talk about the filter design. And in the filter design, we have FIR filter design and IIR filter design. FIR filter design, we're going to talk about the window method. And the IR filter, we have three techniques, which are the pole zero placement, impulse invariant method, and the bilinear Z transformation. So see you, inshallah, in the next week to continue with the DSP lectures. Goodbye.